neutralization reactions. So what are neutralization reactions? Neutralization reactions. In neutralization reactions, acids get neutralized with the help of a base to give salt and water. So these are the reactions between acid and a base to give salt and water. Sometimes the gas is also produced. For example, HCl reacts with sodium hydroxide to give sodium chloride and water. So here HCl is getting neutralized with the help of sodium hydroxide to give salt, NaCl and water. All neutralization reactions are exothermic reactions, so delta H is negative. Delta H is negative. So the examples of neutralization reactions involve the reaction of metal like magnesium with HCl. HCl can be dilute or concentrated to give magnesium chloride and hydrogen gas. So we balance the equation 2HCl. Magnesium oxide can also react with HCl to give magnesium chloride, and now the water will be formed because hydrogen will react with oxygen to form water. Can anyone tell me why magnesium chloride is MgCl2? Yes, magnesium has a charge of 2 plus and chloride has a charge of -1, so we can cross multiply and we get magnesium chloride. Other reactions involve the reaction of magnesium hydroxide with HCl to give magnesium chloride, MgCl2, again water. The above reaction we can balance by putting a 2 over here. This reaction also we can balance by putting 2HCl and 2H2O. Other reactions involve the reaction of sodium bicarbonate NaCO3 with HCl to give sodium chloride and H2O and CO2 gas. We balance the equation. Yeah, it's already balanced. Another reaction of sodium carbonate Na2CO3 with HCl gives sodium chloride and water and CO2 gas. We balance the equation. We put 2 sodium chloride and this is 2 HCl. Now it is balanced. So all these reactions are neutralization reactions. Other example is ammonium carbonate. Ammonium carbonate reacts with HCl to give ammonium chloride and water and CO2 gas. We balance the equation, 2 ammonium chloride, 2 HCl, and this is a balanced equation. Now see how we can find the parent acid and bases of a salt. So finding parent acid and base of a salt. So if the salt is given to us and somebody asks you to find its parent acid and base, so how will you find it? For example, suppose sodium chloride is given to you. So first of all, you dissociate sodium chloride into its ions like sodium ion and chloride ion. Now you take the positively charged ion and react with OH negative, and this will give you sodium hydroxide. So this is the parent base. Now you take the chloride ion and react it with H plus, so it will form HCl. So this is our parent acid. So this is how we can find the parent acid and base. Let us take another example. Suppose this is our salt, sodium acetate, and we have to find its parent acid and base. So we will dissociate it into cation and anion. So this is our acetate ion and this is sodium ion. Now we take our negative ion and we react it with H plus. This will give us acetic acid, ethanoic acid. This is the parent acid of this salt, and this sodium ion we react with OH negative and it will give us sodium hydroxide. This is its parent base. So this is how we can find the parent acid and base of a given salt. Okay, so now we will study the pH curves or the titration curve for the titration of a strong acid with a strong base. Titration curve of strong acid with strong base. Okay, so the pH curve or the titration curve of strong acid with a strong base. So what is an example of a strong acid? Let us take HCl and it reacts with sodium hydroxide, and this is a neutralization reaction. We get sodium chloride and water. So let us take our sodium hydroxide in the burette. This is our burette, and we take HCl in the conical flask. So this is our conical flask. So we have our sodium hydroxide in the burette. This is our sodium hydroxide. Sodium hydroxide in the burette. Whatever we take, we call it as titrant. So titrant is always in the burette. Now our acid is in the conical flask, which we have to neutralize with the sodium hydroxide, and this the solution we take in the conical flask, it is called as analyte. So this is our analyte, and we do the titration. We put phenolphthalein as an indicator to see the end point. Okay, so now let us draw the lines for the pH curve. So this is my y-axis and this is my x-axis. So we will plot pH on the y-axis, and we will plot the volume of titrant on the x-axis. Volume of titrant in milliliters. So what is our titrant? Our titrant is sodium hydroxide. On the y-axis, the pH will start from 0 and the maximum will be 14, and the neutral pH 7 is here. Okay, So now we start to plot the pH of our analyte. So HCl is a strong acid, so the pH will start somewhere from here. Let me draw the neutral line first, so that I have an idea about the shape of my graph. This is my neutral line, pH 7. Okay, so my graph will start from here, this point, and then it will go like these, up, and then like this. It go up and then like this, something like this. Okay, so we see that the midpoint of this sharp rise lies at pH equals to 7. So this point is called the equivalence point. Equivalence point. Okay, our graph started from this point. This is the pH of the HCl, and what happened when we drop NaOH drop by drop in the analyte HCl, so it reacts with HCl to form sodium chloride. So at the beginning of the graph we have HCl and we have sodium chloride. When all the HCl has been converted into sodium chloride, we have a sharp rise in the pH. So this is called sharp rise. This is a sharp rise in pH. Sharp rise in pH. And when the pH becomes sufficiently high, we have here sodium chloride and sodium hydroxide. We are keep on adding the sodium hydroxide. So this line here, we have sodium chloride and sodium hydroxide. So what are the characteristics of this curve? The main characteristics of this curve are that we have an equivalence point at pH equals to 7. This is our first point. Okay, second point, y-intercept. Y-intercept in this graph, y-intercept means where this curve crosses the y-axis. So y-intercept is at pH less than 7, because our analyte is a strong acid, so it is starting from very low pH. Then we saw sharp rise in pH. Sharp rise in pH, right? We saw a sharp rise in pH. Then flattening of the curve. So at the end of the titration we have the flattened line. We call it flattening of the curve. So we have flattening of curve is at pH greater than 7. Flattening of the curve is at pH greater than 7. So these are some of the silent features of the titration curve of strong acid with a strong base. Now if we change the position of our analyte and titrant, we reverse the position, means we keep our HCl in the burette and we keep our sodium hydroxide in the conical flask. So sodium hydroxide become analyte and HCl become titrant. So the shape of this curve will be a mirror image. For example, now if this is my burette and this is my conical flask. Let me draw the conical flask properly. Okay. Suppose this is my conical flask, and this time I have my acid in the burette. This is my acid. So my HCl is titrant. Okay, my HCl is titrant, and my sodium hydroxide is now in the conical flask. Sodium hydroxide is now our analyte. Okay. The reaction remains the same. HCl plus sodium hydroxide gives sodium chloride and water. The reaction remains the same. Now how about the titration curve of this type of setup? We again draw y-axis, and this is my x-axis, and on the y-axis we have the pH, and on the x-axis we have the volume of titrant. So now our titrant is HCl. So this is in milliliters. Okay, pH starting from 0 going to 14, and somewhere here is my middle point, and let me draw the middle point. Neutral is somewhere like this, a line parallel to the x-axis. So now, because our analyte is sodium hydroxide, so my graph will start from pH close to 14, somewhere here. So it will be like this, and then sharp drop in pH, and then flattening of the curve. So now we see the equivalence point is still at pH equals to 7. This is our equivalence point. Equivalence point is a midpoint of this sharp drop. Equivalence point is at pH equals to 7. Our curve started at high pH, so this is the pH of the sodium hydroxide solution in the conical flask, and when we drop HCl drop by drop into NaOH, so NaOH will react with HCl to form NaCl, and until all the NaOH is consumed. And we saw here sharp drop in pH, so this is a sharp drop in pH. This is a sharp drop in pH, and after all the NaOH has been consumed in the solution, we have sodium chloride, and we are still adding HCl, so we have now this flattening. So what are the silent features of this curve? The silent features of this curve are equivalence point is at pH equals to 7. Second, our y-intercept is at pH greater than 7. Okay, then we saw a sharp drop in pH, then what else? We have the flattening of the curve, at pH less than 7. So this was the pH curve, the titration curve of a strong acid with a strong base, when our base was analyte and our acid was titrant.